This is Breanna McGowan for my Lab 5 Part 1 Home Video Lab report on the motion of falling objects. My objective in this lab was to evaluate the motions of an object falling from rest, fast, and another slow falling object from rest, and then relate it to Newton's second law, discussing the impact of gravity and drag forces on the objects. My conclusion was that objects dropped from rest will experience a gravitational and drag force as it falls. The velocity will increase as the object falls and then ultimately reach a terminal velocity in which the two forces will cancel each other out. My first observation was of the fast falling object. I set the axis accordingly as well as the mass, about 2.002 kilograms, and then set the length of the object as a frame of reference for the tracker. It began at time t equals 0 and ended at t equals 0.6. The initial position was at y equals negative 0.002 from the set origin on the axis and ended at position y equals negative 1.378. And here you can see the object falling and each point mass to show where the location is at each point in time. I then modeled the motion accounting for the different properties of the system and designated an arrow to be the gravitational force. You can see the gradual increase in change of position in the beginning, and then it starts to become more constant following Newton's second law of motion and the conservation of momentum. I then placed the observational data as well as the model data on the same graph of position versus time, where the position is in the y-axis. And you can see that while they have about the same shape, the model doesn't accurately predict where the position is at the end of the time period. Next, I modeled the motion with accounting for the drag force. So I have the same specifications, but then I set B, the constant proportionality for drag, equal to 10 to the negative 2.9, which would determine the magnitude of the drag force. So you can see that the drag force will slightly hinder the motion. I plotted the data of this model with the observational data, and you can see that now with the drag force accounted for with the B of 10 to the negative 2.9, that the position of the object at the end of the time period is accurately predicted. My second observation was of the slow falling object. I set the axis here again, and the time began at t equals 0 and ended at t equals 1 second. The position was initially negative 0.001 meters from the set axis origin, and then ended at negative 1.408 in the y direction. I set the point mass at each frame on the same spot on the object, so you can see that it will plot the data on the graph on the right, and it can be used later. I also had set the masses at width of 0.002 kilograms and designated the length of the object so the tracker can calibrate it right, as was done in the first observation. I then modeled this motion with the appropriate conditions and designated an arrow to show the force of gravity downwards. I plotted that data against the observational data, and you can see that it is not an accurate prediction of the motion at all, while it does follow the same overall shape and curvature. Next, I modeled the observation of object 2 with drag force represented, and it has a B of 10 to the negative 2.11 to determine the magnitude of the force, and then I set an arrow to signify it. Here in this comparison chart of the observation 2 versus the model with the drag force, the model can accurately predict the motion, that overall motion, and the end position of the object. So what does this all mean? Well, Newton's second law of momentum conservation applies in these cases. There's a net force that comes to equal 0 as it falls from rest, and then it goes to a terminal velocity. All models do this. Now, what if the object was thrown downward initially? there would be an initial velocity rather than it being zero. With drag, the downward force would decrease, but without, the downward force would increase as gravity acts on it. In both cases, they would come to terminal velocity, but not as quickly as an object dropped from rest. Thank you for watching my report, and I hope you enjoyed it and learned something along the way.